Today I'm going to talk about the inversion of a mechanism. Okay, it's not specific to planar mechanisms. So the concept of inversion of a mechanism does not depend if it is a planar or 3D mechanism, but as we are focusing only on planar mechanisms, on two-dimensional problems, I'm going to give examples only of the inversion of planar mechanisms. So, as usual, what we are going to learn or to have or to be able to do by the end of this lecture or this session now is to know what is the inversion of a mechanism, to be able to define what is the inversion of a mechanism, to be able to differentiate a mechanism from its inversion. So giving a mechanism and giving the inversion, you need to be able to differentiate the inversion. Also, and this is the main outcome of this lecture, is to be able to invert a planar mechanism, but not only inverting the mechanism, interpret what is the impact or what is the effect of the inversion on the motion. Okay, so you will be able at the end of this lecture to invert a mechanism and to discuss the resulting motion of the inversion. So today it will be a little simple. We will follow the outcomes. So first, we will, in the first part, define or give a general definition of what is the inversion of a mechanism. So we'll explain what is and how we can invert a mechanism. It's a quite simple concept, but the most important here is the interpretation of the effect of the inversion on the motion or the kinematics of the mechanism. Inverting a mechanism is quite simple, but the most important is to know what will be the impact of the inversion on the motion of the mechanism. So later we will do this on some examples, and mainly for each example we will focus a lot on what is the impact on the motion, how the inversion change the motion of a mechanism. Okay, so we start with the definition. So what's the inversion of a mechanism? It's quite simple. We have a mechanism. A mechanism is built from links. Links are the elements or the constituents of the mechanism, and these elements are connected together, are using kinematic pairs or joints. And also, one requirement for a mechanism is to have a link as the ground, a link as a reference. So for any mechanism, if we connect links with the joints, we build a kinematic chain. To have a mechanism, we need to consider one link as the ground. Now, in this example, link 1 is the ground. Link 1 is considered as the reference of the motion. Now, inverting the mechanism is to choose another link as the ground, to change the ground, to consider different links or a different link for the ground, to consider a different link as a reference or a frame for the kinematic study. So it is as simple as that. Inverting a mechanism is to choose a different link, here for example link 2, as the ground. Any link can be the ground. So any link can be a good candidate or can be a good possibility to be the ground. So if I have here 6 links, all the 6 links can be a ground. And if I choose, for example, link 1 as the ground, it is an inversion. Link 2 as the ground, it is another inversion. Link 5 as the ground, it is another inversion, and so on. So if I have 6 links, all are good candidates to be the ground. So in all, I can have 6 inversions for the mechanism. If a mechanism has L links, general number, there is L possible inversions in the mechanism. The fact of choosing a different link as the ground, this is the inversion of a mechanism. So if you have 2 grounds, you cancel 1 link, you reduce the number of links by 1. Okay, imagine you have, for example, 5, like this example, 6 links. If you choose 2, link 1 and 2 as the ground, it means they are only they became another rigid body together. Okay, they become one rigid body, so they built a new 1 link. So you will have a mechanism with only 5 links. So it is a different mechanism. If you do it, it is a different mechanism. It's not an inversion. The inversion is always you start from the same mechanism and you choose 1 and only 1 link as the ground. What is inverting is to choose each time, depending on your application, depending on your study, a different link as the ground. Now, I have said there is always 6 possible inversions. This is what is possible. Now, sometimes these inversions can lead to different motions. In that case, we say distinct inversions. And these are the interesting. Sometimes, and we will see some example for each case. Sometimes when you invert the mechanism, there is no substantial difference in the motion of the mechanism. So changing the ground from, let's say, like here. If I consider link 2 as the ground or link 4 the ground, it's symmetric. So it will give me exactly the new configuration and the same type of motion. So both of them will lead to similar inversions. So similar inversions give similar motions. So what I need is really, when I study a mechanism, to see the distinct inversions. The inversions that can lead to different types of motions. Now, for example, here, 5 or 6 here, they are also symmetric. If I ground 5 or 6, both will lead to similar inversions. The motion will be more or less the same. So in grounding 5 or grounding 6, I will get the same kinematics of the mechanism. So I will have 6 links. So if I consider this one, for example, if I will assume that the joints are all the same, okay, and link 5 and 6 are the same, for example, they are both bars or both sliders, the joint, this one and this one the same, so it is a symmetrical one. Yes, in this case they will be symmetric. Now, if I okay, for example, if this left joint is different from the right joint, no, it will be completely different, and in that case I can have distinct inversion. So we need to pay attention a little bit that, okay, there is available inversions in a mechanism, but they are not necessarily all distinct. They are not necessarily substantially different from each other. Some inversions can give similar motion. Some inversion can give similar kinematics. Also, the inversion will interfere with your choice of the input. Now, if your input before was on link 2, now if you consider it as now the ground, you can no more make it input. So when you are going to choose which link will be, or which degree of freedom will be the input, you need to pay attention where is the ground. So the inversion of a mechanism can affect your choice of the input and also the output motion. So when inverting a mechanism, you need later to think how this inversion can affect my choice of the input degree of freedom. So now later we're going to have some examples, and I'm going to insist each time on what is the impact of the inversion on the mechanism itself, and what is the impact of the inversion on the input and output degree of freedom. This is the concept part. This is, okay, a definition of what is a mechanism. It's quite easy to understand what is an inversion. Now, let's go and try to apply this one to a real case. And let's start with a 4-bar mechanism. Actually here, okay, yes. We have here a 4-bar mechanism. A 4-bar mechanism is, of course, made of 4 links, which are the bars. And these bars are connected with 4 pin joints, 4 turning pairs. Now, inverting here a mechanism is grounding 1 link. So each time, for each inversion, I can choose 1 bar and ground that bar. So in all inversions, I will have always 1 bar as the ground, and the 3 others are moving. And for the 3 others, I will have 2 bars that are connected directly to the ground. We'll have fixed axis rotation, and 1 bar will have a general motion. So substantially, I have no difference. Okay, I have no difference. Why? Because I will have always 1 ground, 3 bars moving, and from the 3 bars moving, 2 have fixed axis rotation and 1 have general motion. Now we will see they are not exactly similar. Why? Because here, okay, the inversion will have always a certain effect. Only if all links, for example, if we have here all links, the 4 links are have equal lengths, okay, in that case we will have exactly similar inversions. But as the length of bars is not necessarily equal, They are different from each other. They have different lengths. So in this case, we have some differences in the kinematics of the mechanism. Inversion is not on the nature of motion. The motion of the bars will be always fixed axis rotation for the ones connected to the ground and one general motion. This is the nature of motion. But the inversion here will interfere, will affect the range. How far can one link can go? If a bar will rotate, can it or does it make a full 360-degree rotation? In that case, it is a crank. Or does it, or it cannot complete this full 360-degree rotation. So it is a rocker. It can just go back and forth. So the inversion here will affect just how far can go a link. It cannot affect the nature. The motion will be always, for example, fixed axis rotation. But it is okay. In a certain inversion, I can make full rotation. It is a crank. In another inversion, I cannot make a full rotation, so it will be a rocker. So let's start with the first inversion. So as you expect, the first inversion here. Okay, I have just started with the shortest link. So I block it here, the blue bar, and consider it as the ground. And let's see how the motion of the mechanism will be. So focus a little bit on the red and green bars. So this is a simulation of this 4-bar mechanism, okay, with considering the blue bar, the shortest bar, as the ground. So if you focus a little bit with the red and green bars, they can complete each one a full rotation, a full 360-degree rotation. So both are called cranks. A crank, when you have a body, a bar that can complete the 360-degree rotation. There is no limitation on the range. A bar can rotate and can have any angle. So here the red bar can have any angle and the green bar can have any angle. Okay, so this is the first inversion. The first inversion, I considered the blue bar as the ground. So if I consider here the shortest bar as the ground, I will obtain the double crank 4-bar mechanism. Double crank, why? Because here I have 2 bars, each one is a crank, each one can complete one full rotation. Now mostly, I would say not always, but mostly, these 2 cranks, one will be the input and the other one will be the output. Okay. Now, yes. Now, as I have said, the kinematic diagram is just a representation of the most important things that can help you study the kinematics. So the ground mostly is not represented itself. We don't represent, okay? I don't need to represent the full body of the ground. What I need to represent is only the connections with the ground. So here, what I need is just to represent that I have the red bar has a turning pair or a pin joint with the ground. And also the green bar has a turning pair or a pin joint or a revolute joint with the ground. So mostly when we draw a 4-bar mechanism, it's a 4-bar, but we represent only 3 bars. We represent the 3 bars, the 4 pin joints, and the 2 connections with the ground. So from now on, a 4-bar mechanism will be represented as this one. And here, okay, 3 bars, and the 4th bar is the ground, and it's fixed. Now, this is the first inversion. Now, the second inversion, okay, I will go one by one, choose one by one, and one by one, I will fix it. So for here, I have considered the red bar as the ground. And okay, so the other 3 will move. Now let's see the simulation. Now here, the difference from the previous one, that all the 3 bars cannot complete full rotations. All the 3 bars cannot complete 3 rotations. Okay. For example, the blue bar go back and forth. It cannot have any angle, and the magenta bar also. So here it's called double rocker. Why? Because the blue and the magenta one just go back and forth. They're rockers. When a link rotates but cannot have all angles, is limited in the range, it's called the rocker. So here it's double rocker. And the 2 inputs mostly here are the blue and the magenta bars. Okay. Now again here, when we represent this one, we ignore the bar that is the ground. We don't represent it. What we schematize only the connections with the ground. Now the third inversion, also I will now in the third inversion block the magenta bar, the pink bar, and this will also lead to a double rocker, mechanism. Both can only now the red and the green bars can only go back and forth. And of course, if it is represented, I will ignore the bar that is grounded, and I will only represent the connections, the turning joints, the pin joints that connect the bars with the ground. And now the last one. The last one, I will block the green bar, and in this case, I will have the blue bar, the red bar, and the magenta bar moving, rotating. Now, if I will undertake a simulation, I will see that the blue bar can complete a full rotation. So it is a crank. However, the pink or magenta bar can only go back and forth. It's a rocker. So this is called a crank rocker mechanism. So here we started, or we are analyzing the inversions of a 4-bar mechanism, and depending on the inversion, I can have a double crank, a double rocker, or a crank rocker mechanism. What will be the condition to have there is types of motion, this is tightly linked to the length of links, and this will be studied later with the Grashoff's law, which will be the part D. The inversions of a 4-bar mechanism are similar because they will give always the same type of motion regarding the nature of motion. The motion is always rotation for bars, but it's a little bit different from each others because they can affect the range of rotation for the links, and they can lead to a double crank, double rocker, or a crank rocker mechanism. Okay, and of course we don't need to represent the ground, we only represent the connections with the ground. Okay, the slider crank. The slider crank mechanism is built of 3 bars and 1 slider. And to connect these 4 links, the 4 elements together, we need 4 lower pairs. But the lower pairs, we have 3 pin joints, pin kinematic pairs, and 1 prismatic or translating joint or kinematic pair. So here we have 2 differences. There is 1 difference in the links because there is 1 slider and 3 bars, and there is a difference in the kinematic pairs because we have 3 pin joints and 1 prismatic joint. So grounding one or the other here will lead to 4 different distinct inversions. And we will see now how these inversions are different from each other. Now, there is 4 links, 3 bars and 1. So to do the inversions, I will choose one by one each link as the ground. But the most important, again, is to analyze what is the effect of this inversion of grounding this link and not the other on the motion of the mechanism. So the first one, okay, and this is what is when we say slider crank mechanism, we mean mostly this inversion. This is the original slider crank mechanism. In the slider crank mechanism, the slider is translating along the grounded link. So here I have grounded the green bar. The green bar is fixed, the green bar is static. So the slider is moving along the ground, along the green bar, which is fixed. So the motion here of the slider is a pure translation. Also, the blue bar has a pin joint with the green, but the green is the ground. So actually, the blue bar is rotating with respect to the ground. Here, the blue bar will have a fixed axis rotation. And mostly, depending on the length, but mostly it can complete 1 full rotation, so it is a crank. So that's why I have here the blue bar is a crank. It can complete 360-degree rotation. And the slider is having here to translating reciprocal motion along the ground. So that's why it is called a slider crank mechanism. The pink or magenta bar here is the coupler, is the bar connecting the crank with the slider, and it will have a general motion. This is, when we say mostly in the literature, a slider crank mechanism, we mean this inversion. We mean that the bar on which or along which the slider is translating is the ground. We can also ground the blue bar. Now, if the blue bar is inverted, and also here, this is also in the literature, when we say inverted slider crank mechanism, this is mostly what we mean. We mean this one. The two others remaining that we will see later are also inverted slider crank mechanism, but this is the most popular one, the most used one. So in this inverted slider crank mechanism, in this inversions, in this inversion, the blue bar is fixed. Now, if the blue bar is fixed, now the magenta bar has fixed axis rotation, and the green bar also has fixed axis rotation. So the slider is translating along the green bar that it's self-rotating. So actually here, when we consider the absolute motion of the slider, it is a general motion. Relatively to the green bar, the slider has a translation motion. But relatively to the ground, the absolute motion, the slider has a general motion. It is translating and rotating at the same time. Yes, for the original slider crank mechanism, I forgot to mention it, the inputs. Here, the input mostly is the crank, and the output is the slider. It can be also the opposite. It can be the input, the slider, and the output is the crank. Like, for example, the gas engine, the input is the piston, the slider, and here the crank is the output. We are transforming in the gas engine a reciprocal translating motion to a rotation motion. And we need a crank. We need that here the bar can complete 360-degree rotation. Okay. Here also, mostly the input will be the magenta bar, and the output is the slider. It can also be the green bar, but here mostly the magenta bar used as the input. The third inversion is the magenta bar is the ground. So we block this bar. We have now the blue bar can rotate with respect to the to the pin joint. It's maybe better that okay, I will dominate them. Let's say we have here A, B, and C. Here, for example, A and B and C, and again here A, B, and C. This pin joint. Okay, so here the blue bar can rotate, can make full rotation about B, the pin joint in B. So it is a crank. But also C is here fixed. So actually here it's the opposite. In the previous examples 1 and 2, the slider is translating with respect to the bar, the green bar. Now here is the opposite. Why? Because C is fixed. So the slider cannot move anymore. It can only rotate. So now the green bar is now translating with respect to the slider. It's not the opposite. Okay. So here, what we have said, okay, we have BC or the magenta bar is the ground. AB is a crank. It can complete one full rotation. Now, the slider here can have only one rotation, fixed axis rotation. And the green bar, it has a general motion, but mainly it is translating respectively to the slider. Okay. So you see here that we have different motions, substantially different motion. It's not only the range of motion which is different. The slider in the first one can translate only. In the third one can rotate only. In the second inversion, it can have general motion. And now, in the last one, it will be itself the ground. In the last inversion, okay, we have tried by one to ground all bars. So the last inversion is only possible by grounding the slider. The slider is static. So we have substantially different motion. We in the slider crank mechanism, we obtain 4 distinct inversions. It's not only a range of motion. No, the type of motion is different from one inversion to another. Okay, so here the slider is static. The magenta bar will rotate. Okay, here I would say A, B, and C. So the magenta bar will rotate about C. The blue bar AB will have a general motion. And what is the motion here of the green bar? Only translation, yes. So the green bar is connected to the slider by prismatic joint. So it can have only a translation motion with respect to the slider, which is the ground. So in absolute motion, the green bar can only translate. So these are the 4 inversion of the slider crank mechanism. Now, of course, in the kinematic diagrams, we don't focus on the ground itself. We only consider the connections with the ground. So here, the slider crank, how we represent the slider crank, the inverted slider crank. This is the common one. Now this one here, the slider is only rotating, and this one, the slider is the ground. Now here in this last fourth inversion, we didn't change it. We have completely schematized the ground here because it's necessary. If I remove the ground here link, we will not understand the type of motion. So we will keep it. We will keep representing the ground link here, the slider, only if it is necessary in the analysis or to understand the motion or the type of motion of the mechanism. So these are how we schematize the 4 inversions, and let's see now how the motion or the visualization of the motion. So this is the original slider crank mechanism. So the blue bar, it's a crank. It can complete a full rotation. The slider is only translating with respect to the green bar. Okay. So it is a crank, the blue bar, crank, and the slider red is translating. Now the second inversion, now the blue bar is the ground. So this is the popular or most known inverted slider crank mechanism. So the magenta and the green bars are cranks here. They have full rotations, and the slider has a general motion. It is translating along the green bar, but the green bar itself is rotating. Okay, now the third inversion, where the pink bar is fixed. So the slider here can only rotate. And it is the green bar, which is sliding, translating along the slider. And the last example is the slider is the ground. The magenta bar has fixed axis rotation but cannot complete full rotation. It's a rocker. And the green bar here is only translating. Okay, so these are the first four inversions. Okay, now let's see what's 6-bar mechanism. How many inversions you expect? The mechanism, it's almost symmetric. What I have two ternary links, okay, and two bars from each side. Now, if I ground one, what I will have, okay, if I ground the bottom ternary link, what I will have the ground, one ternary link, and two bars from each side. Okay, imagine this one. Now the second one, if I ground the upper one, what I will have one the ground, one ternary link, and again two bars from each side. So these two will be similar because I will have each time one ground, one ternary link, and two bars from each side. So if I ground the ternary link, any one here, it will give different, it will give similar, not the two together. I ground only one. Okay, but grounding the bottom one or the upper one, it will give similar motion. Why? Because at the end, when I will ground, what I will have is always, so if I ground the bottom one, what I will have is always is a ternary link in the middle and two bars from the two sides. So substantially, there is no difference. Grounding the bottom ternary link or grounding the upper ternary link will lead always to the same configuration, except that, okay, instead of having the ground here from the bottom and the ternary link from the top, I will have the opposite. I will have the three connections from the top and the ternary link from the bottom. So here I will have the first inversion. Okay, in all there is 6, but there is already 2 similar. There is only one distinct from them. So the first distinct inversion here is to ground one ternary link. The second one is the second distinct. I will have to ground one bar, any bar. So there is 4 possible inversions here. grounding, one bar, any bar, but all will lead to the same, to similar inversion, not the same, similar. What I will have always is two bars connected to two ternary links and the ground and one bar. We choose any bar, it will always lead to this configuration. Okay.